In this video, we will go through all of the steps required to set up LVGL on a custom STM32 based hardware platform, all the way from downloading the LVGL libraries, adapting LVGL to our specific board and display, to finally creating and running a simple custom user interface on the hardware and seeing how to manipulate UI entities. LVGL is a free and very popular graphics library for pretty much any microcontroller, processor, and display platform, as well as any interface type such as SPI, I2C, and Parallel. As we'll see in this video, integration in our custom STM32 firmware project is rather straightforward. Make sure to check out the last video on this channel, video number 146, which goes over the essentials of the hardware connections and the basic firmware setup for connecting an STM3287 microcontroller with an LCD, or liquid crystal display. And this is using the STM3287's flexible memory controller, or FMC for short, and this goes through all of the relevant steps of setting that up, as well as then including an ILI9341 pre-made display driver, which then makes that low-level connection between our STM3287, the flexible memory controller, and then the display driver, which in my case happens to be an ILI9341. Keep in mind though, the contents of this video will work on pretty much any processor connected to any display as long as you have the basic drivers set up. The reason for this is that we'll be using LVGL, which is Light and Versatile Graphics Library, and this happens to run on any MCU, processor, and any display type as long as you have that low level set up, the basic drivers, the basic hardware connections. And we'll see exactly how easy it is to set up LVGL in this video. I'll leave quite a few links in the description box as usual. For instance, the LVGL Spring Up tutorials, which essentially is all we're doing in this video, is following these basics and following these tutorials of integrating LVGL. LVGL is super useful because it abstracts most of the UI and display handling, rendering, drawing buffers away from us, and all we have to care about are the calls of, for example, creating the UI or adjusting the UI based on certain controls, and then sending the finished frame buffer to our display using our low-level driver. And we'll go through all of the surrounding setup in this video, but LVGL is really great and free, and it abstracts a lot of stuff away from us. Later on, we will also then be using EEZ Studio, which happens to be a free UI program I found that can auto-generate UI code for LVGL based on a drag and drop editor. I'd also like to give a very special thank you to JLCPCB for sponsoring this video. They are the new sponsors of this channel. They provide excellent services for blank PCBs, anywhere up to 32 layers these days, which is pretty incredible, and very, very affordable PCB assembly services that I also used for this Queen Bee radio controller. If you'd like to order PCBs from JLCPCB, you can use their instant quote service, and if you'd like to order the Queen Bee PCBs, as we saw previously, you can navigate to my GitHub repository and download the manufacturing data, and this is all tailored to JLCPCB. The Gerber files, the component placement file, and the bill of material are all for JLCPCB. At the time of making this video, which is about 2 weeks before Electronica 2024 in Munich, Germany, JLCPCB actually has a booth there and is inviting you to stop by for free gifts, games, and a chance to connect with JLCPCB collaborators and their staff. I'll also be there on November 13th. If you'd like to stop by and say hi, I'd very much appreciate that, and I hope to see you there. We are starting where we left off with video number 146 on the channel, and again I'd strongly encourage you to check that out so you make sure where we are currently at, as I won't be describing that anymore. Essentially, all we've done is connected up the FMC of the STM3287, as well as tested out the driver for the ILI9341, and we've verified our display connectivity to be working, and then we take this as our baseline for our project now. The first step, what we need to do is actually, of course, download the LVGL source files or the libraries. I'll leave a link to this webpage in the description box below, but LVGL is simply available on github.com/lvgl/lvgl. This archive is pretty much all we're downloading, so in Git you can either click download zip or use the usual Git commands to pull this from their repo. On this specific webpage there's also a straightforward download link, and that's all I've done as well. Once you've downloaded that, you can see a fairly large archive of various different files and folders. What we'll be doing is simply copying over all of this into our project and then adding this to the include path. Now on the website here, it says you only need the C and H files under the source directory plus these 2 header files. But there's no harm in simply taking this whole archive and putting it into your project source, as of course when we're compiling, only the relevant files will be taken in. So the way I'm going to do that is I'm going to take the LVGL folder and just place it into source, and I'll select copy files and folders. In the core source directory, we now have all of our LVGL files. Then we would like to add LVGL in the core source folders to the include path. So we go to Project, Properties, navigate on the left-hand side to C++ Build, Settings, and then in these tabs and drop-downs, go to MCU GCC compiler, include paths, and add a new include path by clicking the add button, or simply copy-pasting a previous one and then just changing the directory by double-clicking. So I'm going to do core source LVGL and click OK. Click apply and close. And now we've added the LVGL folder into our include paths. The next few steps we'll go through together, but effectively they're just taken from the LVGL docs, especially this connecting LVGL to your hardware. We're going to go through all of these steps and then finally create our own UI and see if LVGL runs successfully on our board and on our hardware. So far we've acquired LVGL, we've added the appropriate LVGL files to our project, so the next step is create an lvconf.h file. So now let's see exactly what that is. If we go back to CubeIDE, we can see in the LVGL directory we have a lvconf.template.h. So let's open that. The configuration file is one of the primary sources of configuring LVGL for your specific platform. The first thing you have to do is rename the config file and get rid of that template so LVGL knows to use this file. So we just want lvconf.h, and then we want to change this if defined to 1, so we allow LVGL to use this file and to use the contents of this file. It pays off to look through because there's quite a lot of different things you can configure in this particular configuration file. For instance, right at the top, we have the color depth. That could be a 24-bit, 32, 16-bit, or something else. In my case, I'm using an RGB 565 style display and display adapter and driver, and therefore I want my color depth to stay at 16. There are many different defines you can change, and very nicely in the LVG libraries, we have the possible values listed right next to the defines. So it pays off to go through these and check what you need for your project. It turns out for most projects, you don't actually need to change terribly much. In our case, we just have to rename lvconf template to lvconf, change the define to 1, and then of course look through the rest of the file to see if there's anything we have to change. For example, we might be able to change the buffer sizes, the refresh periods of the display, if we're using, for example, operating systems such as FreeRTOS or none at all. And also, which will be useful later on, probably in a future video, is using the STM32H7's DMA2D feature, so we can offload the writing from our frame buffer to the display, for example, using the DMA2D function. But for now, we won't change the configuration at all, we'll just leave it as it is, and then continue. So now we've created the lvconf.h file for our project, now we need to configure some of the rest. But before that, let's go to main.c and we'll include lvgl.h. And let's see if this even builds. So let's go to the little hammer at the top left, click build. And we already see we have these errors, fatal error, LVGL, lvgl.h. There's no such file or directory, so something isn't correctly linked. So the way to actually get around this, you can see we have this if-def structure here. So they're checking if this define is defined, and then they will simply include lvgl.h, which makes sense of how we've defined our include paths. So I'll copy this define, go to Project, Properties, go to MCU GCC compiler, then preprocessor, and click on plus to define an additional symbol, and I'll paste in that define. So I'll click on OK, apply and close, and then I'll rebuild, and hopefully those errors will be gone. Now, the first time you build this might take some time, of course, as there are many different files to build and compile, and then also include in the project. Any subsequent builds will, of course, take far less time. It seems also we need lvconf include simple. So again, we'll go to Project, Properties, add a new define, apply and close, and then rebuild, and hopefully that'll be it. So now hopefully after building, you will have no errors, and we can continue on our path of integrating LVGL. So let's go through this list now. We want to initialize LVG once early during system execution by calling lv_init. So as we've already included LVGL in main.c, remember from the previous video we've enabled the display, we started the backlight PWM timer, we set to brightness 50%, and we've initialized our low-level ILI9341 driver. So after that, after all this basic initialization, we call lv_init. Now, they say initialize driver second. The order I've found doesn't really terribly matter. So you can either initialize your driver before or after. I haven't found terribly much of a difference. Then we have to connect a TIC interface, a display interface, and optionally an input device interface, because LVGL can also handle, for example, touch or any sort of control mechanism that might control the UI. We'll just do a pretty crude implementation later on. So all we have to worry about is the TIC and the display interface. So let's go to the TIC interface section. And we can see here that LVGL needs to know what time has passed to know when it has to redraw or perform certain actions. So there's many ways of doing this. We can either manually call this function LVTick increment, where X is the lapsed millisecond since the last call, or we can use STM32's HAL functions, which is getTick, and just feed that to an LVGL callback, which is exactly what we'll do. And we'll take that here. We'll set the callback for the LVTick function to point to HAL getTick, which returns the elapsed time in milliseconds. So after LVInit, we'll call that function, and now we've sorted out the tick function. Now, of course, if you're not using HAL getTick, if you maybe created your own tick source, such as a timer, you might want to set up your timer as an interrupt or set when the timer has elapsed, and then call LVTickIn on that interrupt handler, for example. As we've set up the tick interface, now we have to set up the actual display interface, and this is where we'll actually make the connection between LVGL and our low-level driver, because LVGL will need to create a frame buffer. So if it's using single buffering or double buffering, we have to define that now. We have to define how the images are drawn, if images are being drawn partially or not, and then also, of course, connecting up our finished frame buffer or pixel buffer to the display and telling LVGL how to transfer the data in RAM to the display. If we click on display interface, we have a few different steps here. The first one is creating a display. So let's go over to that. And all we have to do is copy over this command. So a display, which isn't to be confused with a screen in terms of LVGL terminology, a display is an actual physical display rather than a different UI screen. So I'll copy that over and paste it after the tick callback. And you can see here the display create function requires a horizontal resolution and a vertical resolution. So I've created two defines. For my particular display, I've got 320 pixels width and 240 pixels height due to my orientation. So I'll copy that over. So that's all we have to do is to create our display object, which we'll be referencing later on with a buffer as well, and connecting the driver to this display object. So a horizontal and a vertical resolution. Going back to the LVGL docs, remember after creating a display, we have to define buffers for drawing, after which we'll need to tell LVGL how to send those buffers to the display using our low-level driver. So again, in the LVGL docs, after creating a display, now we go to draw buffers. This becomes a slightly more intricate. There's a couple different ways of doing this. Looking at the LV display set buffers function, we have to pass in a display, which we just created, one buffer, two buffers, the buffer size in bytes, and the render mode. Now, keep in mind, we only need a minimum of one buffer. The second buffer is actually optional. For example, if you want to do double buffering or specific rendering types. What we'll do very simply in this video is simply just use one buffer, and we won't be using a secondary buffer. We'll also be using the partial render mode, as we can see here. So this render mode uses buffers smaller than the size of the display. So if you, for example, have limited RAM in your system, you might not have external RAM available. This buffer uses a minimum of 1/10 of the display size, so the 1/10 of the number of pixels available, which is good in space-constrained systems. Otherwise, of course, if you have plenty of RAM available, or even external RAM, then you might want to use double buffering and larger buffers. So following that on from their simple example, we need to know how many bytes per pixel we have. In my case, I'm using a 16-bit wide interface. I'm using RGB 565, so I have 2 bytes per pixel. And that's exactly what they're doing here. They have this define bytes per pixel, which will just simply translate to 16. And then they're creating a 1 byte size buffer, so Uint 8T type, the display resolution horizontal times display resolution vertical times the bytes per pixel divided by 10. So it's essentially the number of pixels times the number of bytes per pixel divided by 10. And again, this divided by 10 is a minimum. So you might want to have a larger buffer than that. And once you've created your buffer, you pass that to the LV display set buffers function with a single buffer and the buffer size in bytes, as well as the render mode. So I will just copy this over, place the define of bytes per pixel right at the top. Again, this will simply just be 2 bytes per pixel or 16 bits per pixel. And then also paste in this static buffer, which is simply going to be our rendering buffer. But of course, you want our defines. So resolution horizontal times resolution vertical divided by 10 times the number of bytes per pixel. And that will create this very basic buffer. Then scrolling back down in main, after we've created the display, now we want to set the buffer. So I've just pasted in this LV display set buffers function. We're targeting display 1. We've created a buffer which we're pointing to. The second buffer we're not using, so we're simply passing a null pointer. And then we pass the size of our first buffer to tell this function how many bytes are in that buffer. And we're using the partial rendering mode as we saw earlier. Now let's test compile that to see if we get any errors. And this all seems to look okay for now. All right, so now we pretty much just have one main step left. We've initialized LVGL. We've created the display, we've created the buffers and pointed LVGL to this buffer memory space. but now we have to tell LVGL how it can talk to the display. So this is called flushing. And LVGL will call a callback, which we define, so a function that we define, which takes in a number of pixels, how many pixels there are, and then what we have to do in that function is write to the display using our driver, which we looked at in the previous video. So they have an example here. So their callback might be defined something like so. It takes in the display, it takes in the draw size, it takes in the pixel map, so essentially just a list of pixels. And all they're doing is they're looping through this entire area, so all of the pixels, and writing every individual pixel to the display. Now, of course, this is very, very simple and straightforward, but it's also the slowest case because we have to loop through the entire byte array or pixel array and push the bytes individually to the display. Better way might, of course, just be using DMA, so memory to memory or memory to peripheral DMA to do this for us in the background. In that way, we don't have to wait for this function to complete before we can render in the background. But on the STM32H7, with this parallel FMC-based interface, this is actually plenty fast for simple applications, so that's all we're going to be doing here. So what I'm going to be doing is I'm going to be copying this function and putting it above int main, and for the sake of simplicity, I know this isn't pretty, I'm just going to keep the names as we have them here. What they're doing is taking this Uint8 type pixel map and casting that to a Uint16 type because we are using RGB565, also in our example here, so 16-bit wide. Then they're looping through the entire pixel map, the pixel area, and then sending every single individual pixel, so the color for every individual pixel, to the display. And finally, after that, they're calling this LV display flush ready function, which indicates to LVGL that it can modify the buffer again and is not currently in use. So we don't actually have to do very much. All we have to do is replace this put_px function because this is some generic arbitrary function which actually isn't linked to anything. We have to replace this to an actual write to our driver to send data out or a pixel out to our display. So jumping back to our driver, ILI9341.h, we see we already have a draw pixel and a draw pixels function. So if we go into those, all these functions are doing then internally are setting the window, so where to start drawing, and then writing data. And if we follow the write data function, of course, LCD data write is simply a memory map, as we saw in this previous video, because the FMC takes care of this for us. So all we have to do is send our 16-bit pixel data to a specific memory address, and the FMC handles the rest, as we saw previously. So all we have to do is basically just call this LCD set window function, and then we just call the LCD write data function. So I've copied over the LCD window function, but we of course have to modify the parameters we're passing to this. So we're setting the window from an X coordinate to another X coordinate, from a Y coordinate to another Y coordinate. And luckily that's passed to this flush CB function by LVGL contained in this area object. So all we have to do is area X1, area Y1, so that's the start X and Y positions, to the end X and Y positions, which are area X2 and area Y2, like so. Now we have to replace the put_px function, so all I'm doing is pasting the LCD write data command, and all we're sending is the current data at this particular buffer address. So in this case, just taken from the LVGL example, this is the contents at the address where we're currently at buff 16, and then we're incrementing the pointer of buff 16. And this is how we're then cycling through the entire pixel memory map. And then, of course, again, telling LVGL that the flushing is complete. Of course, flush ready has to point to display, not disp, so let me put that in here. And implicit function declaration of function LCD write data. As we can see here in the driver, this is actually static, so it's not actually exposed to the header file, but it simply just calls LCD data write, which happens to be defined in the header file, which we've included in main.c. So what I'm going to do is simply change the write function to LCD data write, and now let's try and compile that again. And there we go, now we have 0 errors and 0 warnings. So having implemented this callback for our specific driver, and as you can see here, this is very, very generic. So in this flush callback, you can put in your SPI driver, your I2C driver, or whatever you're using to interface with the display, with addition of DMA if you want, of course. But this is how we abstract LVGL from the actual low-level hardware. That's why LVGL pretty much runs on any system. Of course, LVGL needs to be made aware of this function, so we have to call this command, which is the LV display set flush callback command. So I'll copy that over and then paste that as our last function. So we're passing in our display, which we defined earlier, and then the name of the function that actually performs the flushing or the writing of the pixels to the display. Looking back at the LVGL docs, we've configured pretty much everything up to point 4. We're not using an input device at the moment, so we jump over to point 6, which is LV timer handler. And this, they say, has to be called every few milliseconds to manage the LVGL timers. And there's a couple of different ways of doing that. So if we navigate to timer handler, we can either do this in our main while loop of the main function, or if we're running an OS, for example, FreeRTOS or similar, we can have that in an OS task. Now, they also give a couple of examples where we can either simply call the timer handler, which returns a time to sleep for or wait for before we call the LV timer handler again. So we can then use, for example, the HAL delay function to wait that much time. There are also, of course, other options. So, for example, there's the LV timer handler run in period or periodic handler. We'll just go with the simplest, which we have here, which is simply we call the LV timer handler. That passes back the amount of time we have to wait before we call it again, and we sleep for that amount of time. So I'll put that in our main while loop and replace the myDelay with HAL delay function, for example. And this is all we have to do for the most basic part to include LVGL in our project. So as you can see, this is super straightforward. And now we can move over to creating a user interface so we can do a very basic test that this actually works. To test the LVGL implementation, we could either simply create our own hand-coded elements that we then display for our display and pass to LVGL, but my preferred method is simply using a drag-and-drop editor. Now, there aren't terribly many available. There used to be one called Squareline Studio, but I think the support for that has now stopped. So I found this other one by Envox, which is called EEZ Studio, which is free and very quickly lets you test user interfaces for LVGL and design them as well. Keep in mind, however, I believe the license for this EEZ Studio and the generated code is under GPL, so that might cause issues if you're trying to either commercially release a product or release a product on a different license, because then it'll have to fall under GPL. So do keep that in mind. But for the sake of just testing and trying something really quickly, I'd recommend just using this for the time being. If you want, of course, you can download this for free. I've already done that. So you can, for example, create a new project, file, new project. We select LVGL as our template, and you need to select the LVGL version. The LVGL version, if we go back to QIDE, go to source, LVGL, we can find under LV version.h, and you can see have version 9.3. So therefore, I'm going to select LVGL version 9.x and go to project. I'll just do LVGL demo and create project. What we have to do to start with is set up our display dimensions on the right-hand side in the properties panel under main. I'm using a 320 by 240 height display. But you can see now it's turned red because also we have to go into this cogwheel in the settings and change the display width to 220 and display height to 240. And there we go. We can close that. And now we have a correctly configured display height and width. Now, just for the sake of testing, on the bottom right, you can see you have various different components. So that's basics such as buttons, labels, text areas, but also inputs and other visualizers, they call them. So we can, for example, drag in one of these spinner elements. I can drag in, for example, a text label, and on the right-hand side, so anytime I select one of these objects on the right-hand side, I can change their parameters, such as the positioning, but I can also change, for example, the text in them. So I could write LVGL demo. If I want to change the specific font, I'll go into default, text, select font, and then change that to, let's say, something larger. And then, for example, I could add in, for the sake of demonstration, one of these sliders on the right-hand side, or anytime you click on one of these parts on the right-hand side, you can see the properties. You can change the minimum, maximum ranges, the type of modes, and so on you can select. So there's quite a lot to play around here. There's lots of different parameters to try out, and all of these elements here are basic LVGL elements that are contained in our LVGL distribution. So there's nothing specific you have to add here. You can also add your own images, you can add your own UI elements, but the ones that are basically here are all from LVGL. You can give them, of course, these elements different names as well in the name text box, but for now, this is all we want to do. Then on the top toolbar on the left-hand side, you can click the little checkbox, click check, and if there's no errors, this all looks okay to this software, then nothing will be output, and then we can click on build. On the top right-hand side, we just saw there was a build successful, and the actual build outputs are put in your user directory under EEZ project, and I think this depends on how you've defined your install. This is where it happens to be for me. So we have LVGL demo here. We go in that, and then go into source. We see this UI folder, and these are the auto-generated .c and .h files we need to add into our project. So going one above, opening QIDE again, what I'll be doing is simply dragging that UI folder into my source folder, copy the files and folders, and then going to project, properties, include paths again, creating a new include path for the UI and clicking close. Then if I go into UI and UI.h, all we have to then do is include UI.h and call UI.init in main.c. So if I go back to main.c, I'm going to include UI.h, and after the LVGL initialization, I'm going to simply call UI init, and then I'm going to build that. After building, you'll oftentimes see this error that LVGL/LVGL is included, so you have to simply change that to LVGL.h. And then if you recompile, that error should at least go away. I believe there's also an option in EZ Studio to avoid that LVGL/LVGL.h include. But now we see we have another error that we see that LV font Montserrat 48 is undeclared. And remember, this is what we selected for our main font for this specific text box over here. The reason is that, of course, we don't want to include every single font if we're not using it. The way we can enable that font is going back to LVGL and going to lvconf.h, and then looking, let's just say for Montserrat, and you can see around line 525-ish, we have all these defines of what fonts we want to use. So if you want to use a font, you have to change that define from 0 to 1. So I'll change 48 from 0 to 1 and click build again. And now this project has built successfully. So all I'm going to do, I have my board connected via an ST-Link, via SeriWire debug. I've got it powered via USB. I'm just going to simply click run and flash this new firmware to the board, and let's see if this now works. Now I've just recorded this with my phone, but this is exactly the UI we just defined and created. And with LVGL handling all of the ticks, we can see we are getting the animation of this spinner wheel and all the UI elements we previously defined. So it looks like our simple integration is already working. Now, of course, with a UI, you want to change maybe the elements. You might want to change the slider position. You might want to change the text or switch to a different screen, which shows different elements and different widgets. And of course, with LVGL, you can do that quite simply. You can either access the elements or these widgets directly and change their properties, for example, changing the actual position, their location, and so on, just programmatically, or you can tie that to the LVGL input controller as well. For now, for the sake of simplicity, just to show you that this is possible, we can scratch the surface on this, we'll just do it programmatically. So what you can do in LVGL, if you navigate on the left-hand side in the project to LVGL source widgets, we can see all the different types of widgets that are available. In our case, we are using a slider. If I go to slider.h, on the right-hand side in the outline, I can see there's an LV slider set value function, and that's exactly the function I want to use. In this very simple case, we pass in the slider object, what we want to change the value to, and if we want to enable animations or not. Changing the value, that's pretty easy. That's from 0 to 100. Well, at least how you define the slider. Remember, we can set minimum and maximum ranges. So min here is 0, max is 100. So the value would be a number in between. Animation, we can set it on or off, but we need to find out what object we have to pass to this. And to find that, I'm going to go back to the UI folder and look at screens.c. And we can see there's this objects struct and objects variable. If I control click on objects, we can see the objects struct actually contains main, which is our main screen, main label, the slide, and the spinner. So the object we actually want to pass is this slider main object, which is contained in this objects container. The way you then would do that is simply call then this LV slider set value. You'd pass in the slider object, the specific value you want to set it to, and animations on or off. The code I've put around here is simply reading pins from the encoders, so I can use button presses to increase or decrease the slider value, and then I simply pass this new slider value using the LV slider set value command. But this little trick of going to LVGL, looking at the widgets, and then looking at the header files to see what functions you can use is something you can do to very quickly attach UI elements to make them dynamic rather than static. Now the code is uploaded to the board and we can see exactly what happened. Again, I took a video on my phone, and this is actually the video we saw right at the start of this particular YouTube video, where I'm controlling the slider using the left and right encoder buttons. So this is then how we can tie LVGL widgets to actually change and be dynamic and move around depending on what we set in our particular program. Thank you very much for watching this video. I hope it was useful, and I hope it showed you how you can very, very easily integrate LVGL into your own custom hardware and firmware designs. Although we did this for an STM32 microcontroller, you saw that this video was pretty much tool agnostic. As long as we have a suitable display driver and a suitable processor that can handle and run LVGL in terms of RAM and flash requirements, we are golden. Please leave a like if you liked the video, comment if you have any questions, and don't forget to subscribe. Thanks again for watching, and I hope to see you in the next video. Bye bye.